Hello, AP Statistics students. This video is all about the computer printout and how to read it and understand it. We're going to be looking at some of the numbers and interpreting them, but we'll also make the regression equation from the numbers in front of it as well. You can see the computer printout here. It's supposed to be like tree, I don't know what it is, like tree diameters or something, but not important. This computer printout has the regression equation here on it already, but most of them don't. And if you ever do an AP problem, they usually don't give you the equation. You have to come up with it yourself. So what we're looking at is usually the coefficient column is what we need right away. The constant part of that is your y-intercept. The constant, just like it says a constant, the y-intercept doesn't change. That's why it's called constant. Then the variable that gets multiplied by your slope is usually listed here. So the constant stays the same. That's your y-intercept. The height is your variable that's going to be multiplied by your slope to get you volume, right? So they're doing height and volume, I guess. Okay, so height, and then this number right here underneath the same place is your slope. So you're always looking for the slope and y-intercept right there. That's really the main two numbers you need because you need your regression equation. The other main one that you're going to need is this r squared shows up, which is your coefficient of determination. And you can, of course, take the square root of that to get r, your correlation coefficient. Those are the main ones. There are some, now once we get going in the year and later on in some more like inference type stuff in statistics, you're going to start looking at these other coefficients over here. We have the standard error for slope. When we do a sample and we get a slope for a regression line, like this one has a slope of 1.54, that's only from one sample out of a whole population. So you have to imagine if you took more samples or a different sample, you would probably end up with a different slope because it's a different sample of people or trees or things from your population. So this number here is trying to inform you of how much the slope could change depending on which sample you took out of that population. So it's a measure of error, right? I have a slope of 1.54, but it could be off by 0.38 plus or minus, right? So that number starts to come into play. Later on, when we do slopes and we're doing testing and inference for slopes, you're going to use the t, and you'll also use this p-value, the probability. This one's 0, so we're going to say there is actually a correlation between height and volume, but that's way down towards the end of the year. The other value that you see over here is the S. You'll see an S come up. This is the standard error for the residuals. So if you looked at all the little teeny residuals that go along with your regression line, this is an average residual. So it gives you a measure of spread. It's just like standard deviation, but in this case, it's with residuals. Okay, so this worksheet is available for our students in the folder, so you can find this, and there's a full explanation of all the different little pieces on it. So it's a nice worksheet, and it goes through the full explanation. It also has another example here, which is also nice. It goes through the whole thing. It points out what everything is. Here's the intercept. Here's the slope. This stuff's all for testing and talking about variation and slope. You got your S for the standard error of the residuals, your variation of residuals, your R squared, which of course you can take the square root of and get your R. We don't need the adjusted, and you don't need these three numbers. Those are not important for this class. I would like to just go over one more in kind of problem format. So this is a study of men, and they took some different statistics down, like their height, their weight, their waist size, and body fat. And this particular readout is from an attempt to have an association between body fat and waist size. Okay, so you can see in this readout, they do not give us our equation. So the first question is, what's the equation of the regression line? So the first place I look is under coefficient. What's my constant? That's the negative 42.734. So I put that as my y-intercept. The waist, because they put this on here, that's telling me what my x variable is, right? So that is my 1.7 is my slope, and that goes along with the waist as my x variable. So I put the 1.7 in as slope and waist variable. And then we're always going to use y hat for regression lines, for prediction lines. So you put a hat on top, but I am going to define this as percent body fat. You can either define these separately like I have here, like, y represents percent body fat and x represents waist size. Or you don't even have to write the y, and you can just put percent body fat right underneath the hat. That's available and allowed as well. Okay, next question is, interpret the information provided by r squared. Well, if we go back up here, r squared is 67.8. This time it's on the top, sometimes it's on the bottom. You just have to find it. 67.8. So I come down here, 67.8% of the variation in percent body fat can be explained by the waist size. The rest is from other variables. You're just saying that we have variation in percent body fat, and by adding on this waist size as my variable, 67.8% of that variation kind of is matched up or controlled by the waist size. The rest is by other variables. Could be, diet and exercise and who knows, right? Just your build or your genetic of the person. That kind of stuff. There's a video that explains what r squared is, so make sure you look for that if you don't know. Okay, and then part C, calculate and interpret the correlation coefficient, which is r. So r squared is the coefficient of determination. This is correlation coefficient. So all you're doing is taking your r squared, which we already know, and taking the square root of it. And now I have my r. Now this is coming from the r squared. So I don't really know if this is supposed to be positive or negative unless I look at my slope. My slope was positive. So I know this is going to be positive as well. If my slope was negative, this would have been negative as well. They should match up with your slope. Okay, so I left it positive. So this shows that the data points are moderately close. 0.82 is kind of moderate. If it was 0.9, I'd start to call it strong, but it's kind of moderate. And the points are like moderately close to the regression line. Now you got to keep in mind, just because this is a strong R value, like a high R value, or even a moderate one, it doesn't mean that the data itself is linear. In order to prove that, or even to kind of show that your data is in a linear fashion, and that a linear model actually is a good idea, you have to look at residuals. The R doesn't do that for you. The residuals is what does that for you, and looking at the pattern. Okay, last question. We're making a prediction kind of, but it's saying calculate the residual. So it wants to find out what's the residual. Well, in order to do that, we need to make a prediction first. So we put in the 35 inches for the waist size for this man, times slope, calculate out. So the regression line says that he should have had a body fat of 16.8%. But it actually, in the question they tell us, he actually had a body fat of 10%. So I subtract those. It's always actual minus predicted, and you'll get your residual of a negative 6.8%. So he had less body fat than the model predicted by 6.8%. All right, that's it for now. Thank you very much.